In this final video, we're going to look a little bit about what happens when the switch doesn't open at t equals 0. It actually just requires a little bit of discussion about the algebra, so we'll look only at the RC discharging circuit. The next thing we'll talk about is how to do this in general. So, we're dealing with RC discharge. And remember what that looks like is an open circuit where we have a VC, and we're assuming that VC is initially non-zero. I'm not going to say VC at 0 because it might not be t equals 0 when it opens. Let's assume it's initially just some voltage V. Now, let's think about this a little bit from the perspective of physical reality. T equals 0 is a convenient place to start measuring time from. But it's not the only time. The capacitor certainly doesn't know that I'm about to open a switch. So really, all that happens is if we were to plot this voltage, and to make things concrete, let's say that at t equals to 1 second we open that switch. Well, would you agree that the voltage will be V until that time, and then start to discharge through the resistor? It certainly makes sense to me, because the capacitor, once again, doesn't know when we're going to ask it to begin discharging. So if this is the case, and our initial expression was Vc of t is equal to V e to the negative t over Rc, then all we need to make sure is that as soon as that switch opens, this argument here is 0. To do that, we introduce the variable t minus, in our case it would be minus 1, and we rewrite it. Vc of t is V e to the negative t minus 1 over Rc. Then, at t equals to 1, t minus 1 is 0, and our expression is going to continue. So what we've essentially done is a horizontal shift. Now, if it isn't 1, let's say it's 2 or 3 or negative 5. In other words, if our switch opens at time equals t0, then we do a horizontal shift by t0 seconds. Vc of t is V e to the negative t minus t0 over Rc. This is especially useful when we have multiple different switches. Let's say that I were to switch one voltage source in and then off, and in and off, alternating back and forth. I will change when this t0 is. Finally, let's look at a more general form. We know that for capacitors, I'm interested in Vc as a function of t. For inductors, I'm interested in IL as a function of t. But did you notice how the equations had essentially the same form? For charging a capacitor, I had Vc was V minus V e to the negative t over tau, or it might be t minus t naught, more generally. And for charging an inductor, it was IL is V over R, or it is some initial I. Now let's put in the full form, where in this case our tau was L over R. But at the end of the day, they look very similar. I have some constant subtracting that same constant, but it may not be, multiplied by an exponential, and we have this t over tau phenomenon going on. We can make a similar argument for discharging capacitors and discharging inductors. So you'll see in many textbooks that we just replace it with a generic variable x of t. Is k1 plus k2 e to the st. And typically, if we want to be even more general, we'll say t minus t0. And then our goal is to find what K1, K2, and S are. In order to do those three things, we make certain notes. X at T0 is X0, which is K1 plus K2. X at infinity, which typically is called X infinity, is just going to be K1. From these two expressions, we can always solve for K1 and K2. Sometimes they're not going to be equal, sometimes they are. We then plug our initial equation and solve for S. Once we've done that, then we can figure out, for whether it's an inductor or a capacitor, how it's going to charge or discharge depending on what's going on. You don't normally see it in this form, because for the most part there are only four equations we need to work with, charging and discharging for capacitors and inductors. However, sometimes it's handy to talk about it in a more general form.